IDALSA is an aluminium recycling plant located in Pradilla de Ebro, Zaragoza, Spain. Since 1984, we have been dedicated to produce high quality of aluminium ingots from the recycling and smelting of waste and scraps. The secondary aluminium production is known for its contribution towards a sustainable and green production, reducing the energy consumption up to 95% compared to primary aluminium, which means a significant CO2 saving benefit. The recycling manufacturing process guarantees the circularity of the resources, waste and scrap, and allows key sectors or customers to decarbonize. But it also imposes new challenges due to new applications, new alloys, and all of it considering a high variability of composition and quality of our scraps and raw materials.
For us in IDALSA, the selection of scrap is a complex problem that doesn't only depend on the chemical composition, but also in external factors such as the availability of materials in the plant and the total cost of production, among others. Here, with more than 100 silos and 300 available scrap throughout the year, there can be multiple combinations of scrap satisfying the standard for our high-quality products, therefore optimizing the selection of scrap considering all relevant factors can be extremely beneficial for us to support our daily decision-making activities.
IMEN is a technology center with more than 60 years of experience developing smart solutions and advanced manufacturing technologies. As part of our expertise, we aim at enhancing sustainability and promote circular economy principles in the industry. In the s-X-AIPI project, we are the main software developers of the IDALSA aluminium use case, where we have developed the AI data pipeline, the self-abilities, and the smart solutions to foster smart and sustainable practices in the recycling applications.
In our process, it's essential that the operator knows the chemical composition of the different type of recipe to be prepared. These recipes are based on the mixture of the different scrap available, so it is possible to evaluate which recipe satisfies better the norm of the desired product. Currently, our recipe generation methodology uses stoichiometric calculation of the chemical composition obtained during the sampling at the reception and control raw material stage, allowing us to infer and approximate the chemical composition of the mixture. With the intelligent decision support system developed in the s-X-AIPI project, a machine learning regressor provides us with a more precise estimation of the chemical composition of aluminum mixture. By using an automatic intelligent system capable of processing a significant amount of data and correlating variables with great precision, we can consider and reduce the bias that arise due to deviation during the fusion process, achieving a better fit and precision of the final composition. With the machine learning model predicting the performance of aluminum mixture, we can cross-check the prediction with our previous theoretical calculation, improving our overall understanding of the process. Apart from this, several dashboards have been developed to visualize the available data and its distribution and evolution over time.
The machine learning model developed by IMEN is based on a multi-output regressor that's composed of random forest regressors. To facilitate user interaction with the technology, the model has been deployed in a web application. In the web, operators can check the associated norm of the product they want to manufacture and select the scraps and quantities they want to use. The model predicts the chemical composition of receipts following a data-driven approach, but operators can also check the estimated chemical composition from the mass balance for double verification. The web contains two other web pages to display the available information in the database in form of interactive tables and charts. Through these charts, operators are also provided with information about the evolution of the data, as well as their statistical analysis.
Another critical aspect for the selection of material is deciding in the first place which scrap should be considered for the recipe. Before the s-X-AIPI project, this decision was solely made based on the human expertise. With the decision support system, a generative model provides us with 3 suggestions of recipes based on requests of products. In this way, we can have 2 3 different recipes satisfying the required order together with information about the expected chemical composition of the mixture, the quantity that will be produced, or the overall cost.
A key point of this solution is that we can also give our feedback of the proposed recipes considering 4 factors: the scraps proposed, the alloys, the chemical composition expected, and the total cost. This information is used by the machine learning framework to adapt the result to our preference.
The generative model we have developed is based on a conditional generative adversarial network, which is conditioned on the product and quantity selected by the users. Moreover, our reinforcement learning algorithm is integrated in this framework to tailor the generated recipes to user preferences. This is done by adapting the reward function to the user criteria collected through the web, which include the scraps and alloys proposed, the expected chemical composition, and the total cost.
The generation of recipes is crucial because it helps us consider all the required materials for a given order. In this way, it is possible to move from a batch-based planning to an order-based planning, which usually includes several batch processes. Eventually, the planning can be extended to weekly or monthly planning as desired by considering all orders of interest sequentially.
The human feedback collected in the multi-output regressor model and the generative framework is used to activate the system's self-management abilities. These abilities, which have been developed following the principles of autonomic computing, are essential to adapt the model responses in dynamic industrial scenarios. By enabling processes like self-retraining and self-fine-tuning, the need for human intervention to manage the system is reduced, making AI more accessible and practical for the industry and the people.